We've now reviewed again the impact defects have on our process yield, reducing, for example, the overall equipment effectiveness and causing internal and external failure costs. In this lecture, we want to look quantitatively at the effect defects have on our goal of achieving continuous flow. Our learning objectives are to describe how rework creates multiple flows through a process, understand how the flow rate is impacted by rework, calculate the impact of defects on the flow rate and resource utilization. Rework means repeating or correcting a process to repair a defect. This could be reprocessing a part with adjusted process parameters or reworking a finished product because the customer specifications are not met. When the IMVP, which is the International Motor Vehicle Program from MIT, visited the General Motors plant in Framingham, Massachusetts in 1986, they found a huge work area at the end of the production line. This area was filled with finished cars, all of which had defects, and all of these needed rework. In other words, the line was back to craft production. And this was clear evidence to the IMVP team of the old-fashioned mass production. Now, here we're seeing our skateboard process again. I hope you're not sick of this. And up to this point, we've not discussed if a defect is produced at any of the steps. Now we have the possibility to rework any parts that are defective at a particular step. So here, for example, at assembly or at sand or at paint, any defective parts can be sent to a rework step. We know how to analyze the process capacity and to identify the bottleneck of the process. And here we saw that paint had 6 minutes per board process time. So since that was the highest, paint was our bottleneck at 10 boards per hour capacity. We also looked at the idea of resource utilization, and in this case, since our demand 8 skateboards per hour, that is less than our process capacity, our flow rate becomes 8 skateboards per hour, and we see that although our bottleneck paint is not working 100% of the time, it still has the highest resource utilization of all of our resources. Now we will include rework into this model. So, what we will see is that internal defect rates impact the workload of the so-called internal factory. And this is often not acknowledged. For example, if we are scrapping lots at one step, the upstream processes then are working to produce defect parts. So if I just drew a little picture of this, we have our process flow, step 1, step 2, and step 3. And step 3 has a problem. It's supposed to be a lightning stroke. Step 3 has a problem. This means any inventory that's going through steps 1 and 2 and then is scrapped means that we're having costs of the resources and the materials that are used to make those defective parts. However, if we can get rid of this problem, then the problem is corrected, then more of the good parts that are being produced at 1 and 2 will make it through part 3 as well. The upstream processes will have less workload per good output. Another example, if we have a process, and we could maybe use our assembly, sand, and paint. So this was our bottleneck at paint. Here at paint. If we have an inspection test here before the bottleneck, so any bad parts come through and here get scrapped, then what we see is that creates more capacity on the bottleneck. So if the good parts that are being produced here make it through to the bottleneck, the bottleneck will be better able to produce those parts because it won't have to deal with these defective parts. So let's look at this quantitatively. Here we have the situation where a proportion of the product through assembly needs to be reworked. And we're saying that this portion is 37.5% of the parts need to be reworked. Now we have a more complicated situation than is covered up to now into this course. We have more than one flow unit. I'm going to draw this in different colors. So we have a demand coming in here of 8 skateboards per hour. 8 skateboards per hour. And 37.5% of the parts, those 8, need to be reworked. So this gives us then a flow through the rework of 3 skateboards per hour. Whereas the good parts that continue through the process will be then 5 skateboards per hour. So let's also say that the rework has a capacity of, has a processing time of 50 minutes per board. This gives us then a rework capacity of 4 skateboards per hour. Now, again, if I draw these through, we have 8 skateboards per hour coming in. We have 5 skates per hour, good skateboards per hour continuing through, and we have a flow of 3 skateboards per hour going through rework. So let's look at our resource utilization. At assembly, there's still 8 skateboards hitting assembly. So 8 over 12 gives us 60% resource utilization. There's no change from what we had before with the earlier example. Now we know, though, that of those 8, only 5 make it through sand. So we have 33% utilization of sand. And before, when we had no defects, that utilization was 53%. Paint, also only see 5. That gives us a 50% utilization. And remember before, with no defects, maybe I should be careful about this, no defects. Here we had 53%, and here we had, and here we had no defects. We had this at 80%. And so before, the paint was our bottleneck with the highest utilization. But we're not done yet. So the rework process is saying here 3 defects per hour, which gives it a 75% resource utilization. So now, with rework and defective parts that are being produced at assembly, where is our bottleneck? And yes, we see it with rework. And here we've written it more clearly for you. We now have a bottleneck at our rework process. Let's increase the demand. Right now, 8 skateboards per hour. Let's increase the demand to 10 2/3 skateboards per hour. So don't forget, this is on average. So on average, 10 2/3 skateboards per hour, or 10.66666 skateboards per hour. Again, 37.5 of the parts need to be reworked. What happens now? Well, we end up with our 10 2/3 skateboards per hour coming in. Of those, we have reworking of 4 boards per hour, and the good parts that continued through are 6 2/3 skateboards per hour. So if we look at the capacities for this, then we end up with assembly seeing 10 2/3 skateboards per hour over 12 is 89%. Sand was seeing a bit more, 6 2/3 coming in. Good parts over 15 is 44%. Paint sees the same 6 2/3 parts per hour for 10, capacity of 10 units per hour. We get 67%. And what we see is our bottleneck is now working full out. So unless you allow for the buildup of inventory at rework, which is what they observed in the GM plant, you cannot work faster than your bottleneck. And if you do, then you're just going to be assembling broken skateboards. I should draw them in red, right? Broken skateboards that need to be reworked here, piling up in this part of your process. So with this example, we've seen how the impact of defects affects more than just the yield loss of production. We see here that the flow is impacted. It causes the bottleneck possibly to shift, or even causing rework to be a bottleneck. So, defects have a direct impact on the process flow. Preventing defects then improves our flow rate. It allows us to better achieve just-in-time performance using pull processes because we're not wasting any time on producing defective products and can better match demand. We also know that just-in-time is supported by smaller setups, which allows us to have lower batch sizes and less inventory buildup. And lower inventories allow us to detect defects more quickly, preventing waste of resources and helping us to have a better culture of identifying and fixing defects quickly.